Welcome to Trane Engineers Newsletter Live. I'm Jeannie Harshaw, and in today's program, we'll be addressing a number of decisions engineers need to make while designing a chilled water system, in the hope that you'll leave with some practical guidance to help you with your future chilled water design projects. Now, the range of topics included in today's program are based on conversations and feedback our application engineers have with customers. To guide you along, we've broken the categories into some common considerations, which leads us into decisions regarding components. Then we'll get into a few advanced design and control questions to consider. To cover these topics today, we have Dustin Meredith, a Trane systems engineer, and Justin Wieman and Mick Schwedler, both from our applications engineering group. So Mick, let's jump right in. How should your chilled water system bypass line be sized, and what length should it be?
Well, to do that, we'll address both primary, secondary, and variable primary flow systems. Let's look at the decoupled or primary-secondary system first. In a decoupled system, the bypass line makes up the difference in flow between the primary or chiller flow and the secondary or distribution flow. The goal is always to maintain more chiller flow than the load needs. When that occurs, there's excess flow in the bypass line. This ensures the desired system supply water temperature is met. A chiller and its pump may be turned off when the chillers remaining online can satisfy the load and flow of the building. So when a chiller and its pump are turned off, there must still be excess flow in the bypass line. That tells us that to turn a chiller and its pump off, the flow rate in the bypass line must be more than the chiller's design flow rate. How much more? Usually engineers use 10 to 15% to ensure that when the chiller is turned off, it doesn't have to cycle back on too quickly. So the bypass line should be sized for 110 to 115% of the largest chiller's design flow rate. In a primary-secondary system, there's an easy way to determine if the decoupler is sized correctly, and that's to compare its size with the pipe going into the largest chiller. Usually the hardest task is finding the bypass line, and it's always between the supply manifold and the return manifold. In this case, the bypass is 10 inches. The chillers here are identical and all have 10-inch lines, so these pipes were selected well. But what happens if the bypass line is oversized? Now, we actually see this occur quite often, and large plants seem particularly prone. In many cases, the bypass line is the same size as the chilled water manifold, and that causes problems. Let's look at an example. There's a 5,000-ton plant at a university, and the air handlers were designed for a 12-degree chilled water delta T, which gives 10,000 GPM. The manifold pipe size is 24 inches. There are 5 1,000-ton chillers, each at 2,000 GPM, with 10-inch pipe. But the bypass line is sized the same as the manifold, 24 inches, which leads to a really low pressure drop. Well, what's the problem? Water is smart and flows to the path of least resistance. So what happens is the cold water leaves the chillers and is flowing through the manifold. A good deal of that cold water flows to the secondary pump, but due to the very low pressure drop in the bypass, some of the cold water seeks that path of least resistance and flows through the bypass line. On the return water side, a similar thing occurs. Return water flows in the manifold. Much of that water continues to the chillers, but some of the warm water, again due to the low pressure drop in the bypass, flows in the deficit direction in the bypass line. Deficit flows from the return to the supply. One symptom of this occurring is that the supply water temperature to the coils is higher than the chiller leaving water temperature. Another symptom is that the chiller closest to the bypass receives mostly cold water, since that water doesn't mix with the warm system return water. This decreases the return water temperature to that first chiller, and it becomes hard to load that chiller. So how can we help this situation if the pipes are already installed? we need to impose a modest pressure drop to keep water from short-circuiting. The first solution most people think of is a valve. But the bypass line is oversized, so the valve will be big and expensive. And at some point, one person will close the valve, and a different person will later open it. Recall that the bypass line in a primary-secondary system should allow water to flow as needed. So a better option is to put an orifice in the line. That can simply be a plate with a hole in the plate. This imposes a pressure drop, but allows water to freely flow in either the surplus or deficit direction. So size the bypass line properly during the design process. Remember to check the drawings. Make sure that the bypass line is smaller than the manifold and the same size as the pipe going into the largest chiller. To impose a small pressure drop, a properly sized primary-secondary bypass line should be about 10 pipe diameters long. If the bypass line is too short, again, there is very little pressure drop and the water tends to short circuit. This causes issues similar to the oversized bypass line. So if your supply and return manifolds are close to one another, one option is to put an orifice in that bypass line. But sometimes the distance is too small. Consider what was done at this chilled water plant, where they came out of the supply manifold with a properly sized pipe, used an elbow, then ran the pipe along that manifold to 2 more elbows to connect with the return manifold. That adds a small pressure drop to keep water from short-circuiting through the bypass. So that's for primary-secondary systems. Conceptually, a variable primary flow or VPF system is simpler to get right. The valve in the bypass line only opens when the system flow rate nears the minimum flow rate of the chiller. So the bypass line and valve only need to be sized for the largest minimum flow rate. Now usually that's the largest chiller's minimum flow rate, but depending on chiller selections, the largest minimum flow rate could be for a smaller chiller in the plant. So confirm all the minimum flow rates. Let's look at an example. On this job, there are 2 different capacity chillers with different design and minimum flow rates. Some of you may think that the pipe for each chiller is larger than necessary, but this is what was on the plans. The largest minimum flow rate is 480 GPM, so the 6-inch bypass line is properly sized for that flow. Since there is a control valve in the VPF bypass line, the length is not critical, but you may want to check out the VPF Engineer's newsletter for information on selecting that valve properly. So in summary, the primary-secondary bypass line should be the same size as the pipe going into the largest chiller and at least 10 pipe diameters long. If it can't be that long, use some piping and elbows to add a little pressure drop. For variable primary flow, size the bypass for the largest minimum flow rate.
A common question regarding the design of ice-based thermal storage is, where do I put the chiller? Should it be installed upstream or downstream of the ice tanks? There are competing benefits on where to install the chiller, and here is a summary of the rationale for whether to put the ice upstream or downstream in the system. With ice in the downstream position, the chillers will be more efficient. However, this position decreases the amount of ice capacity in the system, resulting in either more tanks or more mechanical cooling. This configuration does simplify the layout and the control of the system. Now with the chillers in the downstream position, the efficiency is reduced, but it increases the amount of ice capacity from the tanks. With the increased capacity, you're able to install fewer tanks to meet the same cooling load, or if you use the same amount of tanks, you can downsize the chiller. Now let's take a look at an example and the impact on the system depending on the chiller location. In this example, a building has a design day on-peak cooling requirement of 8,500 ton-hours with a 75% diversity factor, which is the peak load divided by the average load during the 12 on-peak hours. The system flow rate is 1,200 GPM, and the cooling coils are selected for a 20-degree delta T to meet the 941 peak tons. However, there is limited space available which limits the installation to a maximum of 20 ice storage tanks. We will first consider if the ice storage tanks are located in the downstream position of the chiller. In this configuration, the tanks will be cooling 50-degree fluid down to 40. At these conditions, each tank is capable of providing 144 ton-hours at a discharge rate of 16 tons per tank. So locating the tanks downstream allows the chiller to receive the warmest entering fluid temperature and to produce a higher leaving fluid temp. And this results in increased chiller capacity and improved efficiency. In this example, the chiller cools the fluid from 60 down to 50 degrees, and by utilizing a variable speed drive, the chiller can operate efficiently at a 0.4575 kilowatt per ton. The downstream ice storage tanks cool the fluid from 50 down to 40, and at these temperatures, the 20 ice storage tanks in the example can provide 2,880 ton-hours of cooling, leaving an on-peak cooling requirement of 5,620 ton-hours. That must be satisfied by the chiller. The peak discharge rate for the tanks was determined to be 16 tons per tank, and with 20 tanks, that allows for a total ice discharge rate of 320 tons. The remaining 621 peak tons will be handled by the chiller. At a 0.4575 kilowatt per ton, that results in 284 kilowatts. Now, let's look at the same example with the tanks installed upstream. In this configuration, the tanks will be cooling 60-degree fluid down to 50. At these conditions, each tank is now capable of providing 174 ton-hours at a discharge rate of 19 tons per tank. This configuration allows the tanks to receive the warmest entering fluid temperature and operate at a higher leaving fluid temperature. And this results in increased storage capacity. Using this same example, the upstream storage tanks cool the fluid from 60 to 50. And at these warmer temperatures, the 20 ice storage tanks can provide 3,480 ton-hours of cooling, which provides over 17% more capacity than when these same tanks were located downstream of the chiller. This reduces the on-peak cooling requirement that must be satisfied by the chiller to 5,020 ton-hours. The discharge rate has also increased to 19 tons per tank for a total ice discharge rate of 380 tons. With this increased rate, the chiller now only needs to condition 561 peak tons. With the chiller located downstream, however, it must cool the fluid from 50 to 40 degrees. These colder fluid temperatures degrade the efficiency of the chiller to a 0.5932 kilowatt per ton. So this configuration reduces the on-peak cooling load that must be satisfied by the chiller. However, it is operating less efficiently, and the on-peak draw of the chiller is increased to 333 kilowatts, nearly 15% worse than when the tanks were located downstream. In summary, locating the 20 ice storage tanks downstream of a chiller with a variable speed drive rather than upstream reduced the on-peak electrical demand by an additional 49 kilowatts. In the past, you may have heard of the Latin word SIC. This was an acronym to help you remember where a chiller should be located. It stands for screw or scroll compressor, then ice, and then centrifugal. It implies that with a screw or scroll chiller, you should install the ice downstream, and with the centrifugal, the ice would be installed upstream. Historically, this has held true. However, with recent advances in chiller performance and operation, the addition of variable speed drives, there are many advantages to always installing the ice downstream of a chiller.
With the trend to design systems for higher delta Ts, many wonder whether this design practice can be applied to existing coils originally selected for lower delta Ts. Let's briefly discuss why we would want to entertain this idea and then provide some direction through a series of examples. If we keep all the coil's physical properties the same, we know that we can decrease the flow if we design to a higher delta T. But how does a jump from a 10-degree delta T to a 15-degree delta T affect our power consumption? Pump affinity laws tell us that pump power decreases with the cube of the flow rate. By increasing the delta T by 5 degrees, These laws tell us that the corresponding reduction in flow rate will yield a significant reduction in pump power, up to 70%. Now this is idealized, but it should provide a feel for the power reduction possible with higher delta T's. This reasoning is what has led industry to recommend higher delta T's. Here's an excerpt from ASHRAE 90.1 2016, which requires a chilled water delta T of at least 15 degrees. Now this is a requirement for new systems, but we can evaluate this guideline for system retrofits as well. Delta T and flow rate are variables. They should be selected to design an efficient and flexible chilled water distribution system. If the chiller is producing colder water, it will use more power. But in many applications, the system energy, the energy used by both the chiller and the pumps, will be less. It's a trade-off, more chiller power for decreased pump power. Some claim that reducing flow rates and expanding temperature differences is only for new systems. As we'll see, this concept can also work well in system retrofits. Before diving into some examples, let's see how higher delta T's affect coil heat transfer. The amount of heat transferred from a cooling coil is dependent on the equation UA-LMTD. With an existing coil, the coil area is constant, and our primary interest is in the LMTD term, or log mean temperature difference. This temperature difference is an asset of an existing coil that can be exploited. By changing the entering water temperature, the valve controller modulates the valve, which in turn modulates the water flow rate. The result is that the same amount of heat is transferred across the coil. Said another way, to satisfy the same load, if we put less water at a colder temperature into the coil, the water will often leave warmer than it would have if operating at its original conditions. For the examples that follow, we'll select a coil for a 10-degree delta T. Keeping the same air conditions, capacity, and physical coil features intact, we will then evaluate the effect of changing the entering water temperature to increase the delta T above 15 degrees. Unless otherwise noted, the examples will all assume that the coils have two-way valves. Our first example is a large 40 square foot air handler. This 6-row coil was originally selected to deliver 783 MBH. The entering water temperature is 45 degrees and 156 GPM is required. The water leaves the coil at 55 degrees, giving a water temperature rise of 10 degrees. In this example, we want the same airside performance from the coil. So let's see what happens when we keep all of the physical coil properties the same and select a coil with equal capacity but differing delta T. We'll accomplish this by lowering the entering water temperature until we exceed a 15-degree delta T. Since the air conditions are the same, this coil still must be able to produce the same capacity, 783 MBH. So what if we send the coil colder 41-degree water? In response, the coil valve modulates to allow less of that cold water, reducing the flow rate to about 99 GPM. This results in an increase in the leaving water temperature to nearly 57 degrees, giving a water temperature rise around 16 degrees. In other words, by reducing the supply water temperature to the existing coil, we've reduced our GPM by 36%. This reduction in flow will yield substantial pump energy savings. And with a higher leaving water temperature from the coil, we will minimize the impact this higher delta T has on the chiller. Now let's run a similar comparison, this time with a small central station air handler. In this example, we've selected a 6 square foot 8-row coil. To meet capacity with a 10-degree delta T, our flow must be 22 GPM. Keeping the airside conditions and the coil's physical properties the same, we can see that a 15-degree delta T drops our flow down to about 14 GPM, or a 34% reduction in flow. However, we now need 38-degree entering water to meet this higher delta T. This 7-degree drop would really work the chiller hard, and overall system energy use would need to be reevaluated to see if this change is even worth it. Note also how our leaving water temperature actually decreased. This wasn't expected, and is why we had to lower our entering water temperature so severely. Why is this coil so much worse than the other? Notable differences include size, flow, and capacity, but what are the primary factors contributing to a decrease in entering water temperature? And why did the leaving water temperature actually decrease with a small air handler? The answer is tied back to fluid velocity, or more importantly, the Reynolds number, which is a measure of how turbulent a flow is. This graph plots Reynolds number along the x-axis and the coil heat transfer factor along the y-axis. When the Reynolds number drops below 10,000, the coil's heat transfer factor begins to level off. At Reynolds numbers below 5,000, the heat transfer factor drops considerably. In our small air handler example, we are operating at about 3,600, well into this drop region. You might have noticed how the heat transfer factor rapidly increases in the laminar region, where Reynolds numbers are below 2,100. Don't confuse this increase with an increase in capacity. The heat transfer factor is not the only variable used in the calculation of capacity, and in this laminar region, capacity will be reduced when compared to the other regions. Keep this quantity in mind. Justin will cover Reynolds number in more detail with the next topic. This issue is characteristic of smooth coils. For new systems, or if coil replacement was an option, what if there was a way to increase the heat transfer in this region? Let's now see what would happen if we enhance the coil tubes on the small central station air handler using turbulators, for example. In this case, our small air handler coil with turbulators results in performance similar, if not better, than the coil in our large air handler. We now only have to lower the entering water temperature by 4 degrees and get the benefit of almost 2 degrees of increased leaving water temperature. This results in a 37% reduction in flow with a minimized impact on the chiller. This begs the question, would it make sense to replace a coil with one that uses enhanced tubes? To answer this question, the initial cost for a replacement should be balanced with the ongoing savings associated with a higher delta T, made possible with an enhanced tube coil. These examples provide us with a few conclusions. Higher delta T's work great with coils that have higher fluid velocities, coils with higher Reynolds numbers in particular. If the tubes are or can be enhanced, higher delta T's can be used with smaller coils while minimizing the impact on the chiller. If your existing job has enhanced tubes, you should definitely consider higher delta T's. Not only are the concerns with lower flow rates diminished, but the reduction in fluid pressure drop is even more substantial. Here's a rule of thumb when evaluating retrofit coils for higher delta T's. For every 2-degree reduction in entering water temperature, expect about a 1-degree increase in leaving water temperature. Of course, this only applies to coils operating in the turbulent region or with enhanced tubes.
Thanks, Dustin. Now let's move into some of the component-specific decisions HVAC designers need to consider. So back to you, Justin. Why is it important to stay between the minimum and maximum flow limits?
Oftentimes, we are asked, why do you have a minimum and maximum flow requirement for your chillers, and do I have to stay between them? The requirement for the range of flows is not unique to any one manufacturer. All chillers have a minimum and maximum flow rate that should not be violated. These ranges vary between manufacturers' equipment as well as between different chiller types. And there are a few reasons that these values are defined and published that we will discuss. The first reason is based on the chiller performance. We want to ensure that the chiller has optimal performance to reduce energy usage. The second is to ensure proper stability. And finally, reliability of the unit. We want to ensure that the chiller will last for the many years down the road. Let's start by explaining the performance impacts of violating the min and max flow rates. But before we do that, we'll walk through a couple fundamentals regarding chiller performance and efficiency. There are 2 factors that impact the chiller performance. The first is the amount of load the chiller has to satisfy, and the second is the lift a compressor must generate. The amount of lift is the difference in refrigerant pressure between the evaporator and the condenser. The refrigerant pressures are proportional to the temperature of the refrigerant. Therefore, the colder the evaporator and the hotter the condenser refrigerant is, the higher the lift. For a properly functioning system following the min and max flow rates, lift is also proportional to the leaving evaporator and leaving condenser temperatures. Let's discuss what I mean by a properly functioning system within the range of acceptable flow rates. Here's a graph of a tube's heat transfer coefficient versus the velocity of the fluid in the tube, as well as the associated Reynolds number. The velocity is the scale on the bottom of the graph, and the Reynolds number is the scale on the top. You'll routinely find the min and max flow rates defined in terms of velocity, specifically feet per second. However, it's actually the Reynolds number that manufacturers are concerned with regarding tube performance. The Reynolds number is a measure of how laminar or turbulent the flow of a fluid is. If you have a highly turbulent flow, the Reynolds number will be high and the corresponding heat transfer or performance of the tube will also be high due to the rapid mixing and surface contact of all of the fluid molecules. Low Reynolds numbers indicate laminar flow, where tube performance is significantly degraded. Laminar flow is identified at a Reynolds number less than 2400. Manufacturers will try to set the minimum flow rates around a Reynolds number of 8,000 or above. 8,000 is considered a transitional flow between laminar and turbulent and is shown with the red line on the left. If you operate your system below the minimum flow rate in a laminar flow region, the tubes have a very low heat transfer coefficient and cannot effectively transfer the energy between the water and the refrigerant. When this occurs, it takes much colder refrigerant to deliver the desired chilled water supply temperature, thus increasing the lift on the chiller and the overall kilowatt usage. For the condenser side, same situation occurs. However, you end up with a higher refrigerant temp as the tubes cannot efficiently transfer the energy from the refrigerant to the water. And there is an additional concern for very low flow rates as well, and that is more targeted towards the condenser. The other concern has to do with tube fouling in an open condenser loop. As the flow becomes laminar, the potential for tube fouling, such as calcium buildup, increases. And the higher the tube fouling, the less effective the tube is at transferring the heat. So chillers also have a maximum flow. A typical value for maximum flow is around 11 feet per second, as shown by the blue line on the right. We'll discuss the implications of violating the maximum flow later. Lastly, I wanted to point out that the green circled region is the range between about 5 to 7 feet per second. This is the range that chillers are commonly selected in because it minimizes the chiller's pressure drop while still providing good tube performance. So that addresses the performance concerns. What about the stability concerns? The first 4 issues on this list are all related to the tube performance we just discussed based on violating the minimum flow. If your tubes do not effectively transfer energy to the chilled water supply, it will take colder refrigerant to meet the supply temps. Without proper controls, this could result in a temperature that drops below the minimum allowable refrigerant temperature, and if that occurs, the unit will shut down in order to protect itself from the potential of freezing up tubes. And as my colleague Mick always says, every chiller has the capability to freeze water once. Chillers also have a high pressure cutout set for the condenser so that the same situation of the chiller shutting down can occur on the condenser side if the flow rates are too low. For a centrifugal chiller that is dynamic compression, you also have the concern of causing the unit to surge. And surge occurs when the amount of lift needed to be generated exceeds the amount of lift the compressor can actually generate. This results in refrigerant flowing backwards, which is called surge. And surge creates unnecessary wear and tear on equipment, and the unit will shut down. Additionally, the increased lift, regardless of the compressor type, will cause the chiller tonnage to reduce, and you may not be able to satisfy your building load. Finally, if your tubes are not performing properly and you lose heat transfer, you will begin to see the chilled water supply temperature increase and not provide the desired temperatures to the cooling coils. Everything we have discussed has been related to having minimum flow rates set. So, why is there a maximum flow rate? For one, as your flow rate increases, so does the pressure drop on the system, which affects the overall performance. However, the main reason there's a maximum flow rate set is to protect the integrity of the tubes. At high velocities, such as 11 feet per second and above, the potential for tube erosion increases drastically. And tube erosion will reduce the life of the tube and cause excess maintenance. So to summarize, chillers have a minimum and maximum flow rate limitation that should not be violated for 3 major reasons. First is chiller performance. Staying within the range of flow rates will allow for efficient operation of your chiller. Second is stability, enabling your chiller to operate in a manner to avoid disruptive shutdowns and loss of temperature control. And finally, reliability, to ensure that your chiller will last for the decades it was designed to last for.
A common component that has been traditionally included in constant flow hydronic systems is a balancing valve near the pump discharge. The valve can be independent or it can be combined with other components in what's known as a triple duty valve. Let's see how such a balancing valve works with today's systems. The first question we need to ask is, what does a balancing valve do? A typical balancing valve simply creates back pressure so the pump will provide the appropriate flow. In other words, it's included to throttle the flow. So why are balancing valves needed near the pump discharge? For starters, pumps are often oversized. For example, a pump may be selected to provide 115% of flow as a safety factor. To operate the pump at the correct flow, a balancing valve can be used to throttle the pump. Next, if the system has been balanced to ensure proportional flow through each load, the pump's flow will be different after balancing. Again, a balancing valve can be used to throttle the pump back to the correct flow. Assuming the pump is oversized, our ultimate goal is to adjust the pump flow down. There are a number of ways to accomplish this goal. The first is, of course, the balancing valves we've been discussing. They are very effective at throttling the flow. Once installed, however, these present a permanent restriction in the system which wastes energy. A slight variation to the balancing valve is a triple duty valve. This valve type combines a balancing valve with other components needed on the discharge side of a pump, including a check valve to present reverse flow and an isolation valve for servicing. A check valve and a means of isolating the pump are still always required. As we will see, however, we may no longer need the balancing valve functionality. Even if fully open, a triple duty valve will carry a pressure drop penalty. Thus, consider separate components in lieu of triple duty valves to minimize energy use. So what other options do we have to adjust flow? The next option is to trim the pump impeller. That is, slightly change the impeller dimensions in accordance with the pump manufacturer's instructions. Think of this option as reselecting the pump to provide the actual design flow. The main problem with this approach is that few will ever go to the trouble to actually perform the modification. It's just too easy to include and adjust a valve. Another problem is that a trimmed impeller can never return to its maximum pump flow rate and pressure if such capacity is ever needed. You might now be wondering, why not just slow the pump down? Good question. If we include a variable speed drive, we can avoid the hassles of having to disassemble the pumps and have that pump down for hours and days while the impeller is being cut back. With a variable frequency drive, for example, we can simply lower the operating hertz setting in the VFD via the keypad. So this begs the question for existing systems. Should folks consider eliminating the balancing valve near the pump discharge and replace it with a variable speed drive? The reality is that variable speed drives have come a long way since their introduction. In the past 10 years or so, they've become much more reliable and their costs have come way down. For today's jobs, it's probably fairly easy to justify the cost of a variable speed drive compared to the energy penalty of having a permanent pressure drop included in the system, as is the case with a balancing valve. One final caution, however, take care when applying a variable speed drive to an existing motor. Consult the drive and motor manufacturers to ensure compatibility. If not compatible, the motor may need to be replaced. For simplicity, we've focused on constant flow systems thus far. So how about a variable flow system? This one's simple. We've already discussed how a variable speed drive is probably your best bet. So just use the drive that's present to adjust maximum or design flow. So that leaves us with our final question. Are balancing valves at the pump, and by extension, triple duty valves, needed? No. There are more efficient, more accurate, and easier to commission options that should be considered instead. Now that we have that question out of the way, what is the optimum way to adjust flow? Pump manufacturers tell us that it's more efficient to adjust pump flow through a speed change while simply leaving the impeller with a larger diameter. This makes sense for a variety of reasons, including effort, efficiency, and limits associated with trimming the impeller. Of course, this focuses only on the impeller efficiency. Keep in mind that variable speed pumps have losses internal to the variable speed drive. With all things considered, however, A variable speed pump will likely yield the lowest overall energy requirements.
Next, should pumps be dedicated or manifolded? We'll cover the advantages and disadvantages of each. But let's look at dedicating pumps first. If pumps are dedicated, they would look like the two diagrams shown. However, in the dedicated configuration, if a pump is not available, the chiller can't be operated. The biggest advantage of dedicating pumps is simplicity of selection and operation, since the pump is selected to serve the flow rate and pressure drop for its chiller. Disadvantages include lack of redundancy. But if the units are identical, redundancy can be achieved by adding another pump and piping it so that that swing pump can serve either chiller. Here's a configuration with a third pump that, with piping and valves, can serve either chiller. Note that each pump has a check valve. With the pumps dedicated to each chiller, water can only go from left to right. Now, a few people watching this just thought, wait, those pumps are manifolded. Why don't we just allow them to operate that way? Great question. The difference is once the pumps are fully manifolded, isolation valves are required at each chiller to keep the water from flowing through the inactive chiller. For manifolded pumps, let's look at the disadvantages first. Let's start with a pressure drop challenge. Here, two chillers were selected and had different design pressure drops, 12 feet and 20 feet. The problem is that water is still smart. It will flow through the path of least resistance, which is lower pressure drop. In this example, when both chillers are operating, using the affinity laws, the flows change until the two pressure drops are equal at 14.3 feet of head. At this pressure drop, the 500-ton chiller will have 9.2% more flow than selected, and the small chiller will have 15.3% less flow. This means that at some point, chiller 2 will not be able to load fully unless its supply water set point is decreased. Additionally, if the return water temperature is at design, chiller 1 won't be able to make its set point. To reduce system complexity, select the evaporator pressure drops as close as possible to one another. If the pressure drops differences are significant, a balancing valve must be placed in series with the evaporator with the lower pressure drop. In this case, a balancing valve imposing 8 feet of pressure drop can be installed in series with the chiller 1 evaporator. Now, let's look at the advantages of manifolded pumps. A distinct advantage is that any pump can work with any chiller, so a high level of redundancy is realized. Also, in a VPF system, the pump design and selection can be optimized since the number of pumps does not have to equal the number of chillers. Finally, manifolding pumps allows overpumping of chillers in systems experiencing low delta T syndrome. Now, some systems experience low delta T at the coils, and this causes issues in a primary-secondary system. Let's look at an example. Two 500-ton chillers are each selected to take 750 GPM of water from 56 to 40 degrees. There are some three-way valves and dirty coils in the system. In addition, some of the air handler controllers aren't working properly. The result is that the return water temperature from the system is only 50 degrees, even though the flow rate is 1,000 GPM. Note that this system load is only 417 tons, so chiller 1 has the capacity to handle the load. If only one chiller and its pump is operating, there is 750 GPM of flow through the chiller. Since the return water temperature is only 50 degrees, the chiller can only deliver 313 tons. So the second chiller and its pump must be added to help satisfy the remaining flow and capacity required. While the flow issues are now overcome, there are a number of pieces of bad news. Compared to one chiller operating at 80% load, two chillers may not operate as efficiently at this lower 40% load on each. But even if the chillers operate more efficiently, the primary pump energy doubles, the condenser water pump energy doubles, and there are now 2 cooling tower fans and cells operating. So in primary secondary systems with constant speed pumps, this step function increase in ancillary equipment power often results in inefficient system operation. Remember that this system load is only 417 tons, so Chiller 1 has the capacity to handle that load. In a system with manifolded pumps, the operator can overpump chillers by allowing pump speed to increase to deliver the 1,000 GPM needed. All overpump means is that there is more flow going through the evaporator than the design selection. The chiller has more than enough capacity to deliver 417 tons given these conditions, and the plant can respond to reduced return water temperature without having to enable another chiller. This also keeps that ancillary equipment off. Here's a schematic of the overpump chiller. Note that we mentioned it was the manifolded pumps that were important. This can work in either a variable primary flow system or a primary secondary system with manifolded pumps with variable speed drives. One more thing, overpumping is not a fix for low delta T syndrome. As Bill Code, ASHRAE presidential member, pointed out in his August 1998 HPAC article, correcting the return water temperature problem must take place in the system at the coils, not the chilled water plant. For information on mitigating these problems, see the 2017 ENL on myths or realities, or the article shown on the slide. So, should pumps be dedicated or manifolded? Dedicated pumps are beneficial if the chillers have different capacities or pressure drops. But manifolded pumps have a lot of advantages, including redundancy, flexibility, and ability to respond to different system operation points. For that reason, we see many systems designed using manifolded pumps.
A chilled water system decision that is becoming increasingly popular is the choice between conventional and pressure-independent control valves. In this section, we will introduce how these valve types differ, the different types available, and conclude with a case study. So what is a pressure-independent control valve? If you've ever sized a conventional control valve, you're probably familiar with the flow coefficient calculation shown. To select the appropriate valve, one must first determine the required flow coefficient, given a flow rate through the coil and a desired pressure drop across the valve. The valve is selected to have an authority that will provide accurate and stable control. Rearranging this equation, we see that flow is dependent on the pressure differential for a given value. Valve performance would be fine if the pressure differential across the valve was always at the selection condition. But during operation, other parts of the system are constantly changing, which causes the pressure at the valve to also change. With a fixed coefficient, the flow, therefore, has no option but to also vary. Even if nothing has changed in a particular space, the control valve must now modulate to adjust flow in response to these system pressure changes. Thus, the controllability of a conventional control valve is significantly affected by variations in pressure. What if there were a separate device that absorbed the system pressure variations so that the control valve always saw its selected pressure differential? It should always have its selected control authority, it would always pass only its designed flow when wide open, and it would be easier to control stably. In other words, what if we could make the control valve pressure independent? A pressure independent control valve should yield a number of advantages. The valve control should become much more stable. To maintain space temperature, the actuator no longer has to adjust for varying system pressures. This will extend valve and actuator life. Also, stability positively impacts system efficiency. Since the valve is now controlling flow directly, the accuracy should improve. They are much easier to select. Simply choose a valve that provides the needed GPM. A flow coefficient calculation is no longer needed up front. And because pressure-independent valves automatically balance the system, no separate balancing valve is required. Thus, they are much easier to install. Stability and accuracy are particularly important. Anything that causes the valve to lose accurate and stable flow control under any operating condition will result in lower than desired average waterside delta T. Of course, lower delta T can result in a dramatic increase in pump power and a decrease in chiller plant efficiency. So how do pressure-independent control valves work? First, recognize that there are two types of pressure-independent control valves, mechanical and electronic. The mechanical variety basically combines two valve types into one. First, a pressure regulating section. As system pressures change, the pressure regulating section automatically adjusts to keep the pressure constant across the control section of the valve. Next, the control section of the valve is modulated by the control system to adjust the flow to the valve as space conditions change. On the other hand, an electronic pressure-independent valve doesn't actually maintain a constant differential pressure across the control valve surface. Instead, it achieves independent control similar to a pressure-independent VAV valve. It includes a flow meter in series with a standard control valve. It then calculates the instantaneous flow and pressure across the valve and continuously recalibrates the control coefficients to provide stable and accurate control. There are a number of advantages associated with mechanical pressure-independent valves. They are more compact in size when compared to a conventional control valve, plus flow limiting valve package, or to their electronic counterparts. Depending on the manufacturer, they can be paired with any rotary actuator. They are easy and straightforward to select, and there are no additional controls or programming required. Likewise, the electronic variety has a number of advantages. They have the potential for lower hardware costs, they can provide actual load measurements, and they are programmable for alternative operation methods. For example, the valve could be set up to limit delta T, not flow. Also, they can be set up for backnet communication to enable data sharing. These advantages have to be weighed with the additional complexity. For example, special software will be needed to set up and maintain the valves for the life of the product. Also, operators will need to be trained in this software, and it will need to be kept up to date. So now that we understand what a pressure-independent control valve can do for a building system, let's look at a case study. A high-rise building in Atlanta was identified as a good candidate because it had some existing control problems. Once those problems were identified and resolved, one floor was retrofitted with a pressure-independent control valve and was compared to a floor that had kept the existing conventional control valve. Here are the results. First, notice how both valves are able to control to a high chilled water delta T. In other words, a pressure-independent valve isn't required to achieve higher delta Ts, but notice how the conventional control valve is less stable than the pressure-independent valve. In particular, notice a considerable variation in valve position for the conventional valve. As we've discussed, stability will improve delta T. Also, less action on the actuator should improve actuator reliability. So let's summarize this discussion. We've demonstrated how pressure-independent valves are more stable and more accurate, which should improve system delta T. We've also seen how pressure-independent valves can make valve selection much easier. A lot of conventional valves are poorly selected, and it's highly unlikely a poorly selected valve will provide good control. We've also seen how pressure-independent valves are easier to install, as they eliminate the need for balancing valves. And considering the price premium has been steadily dropping, pressure-independent valves might be cost neutral if all costs are considered. So are pressure-independent valves worth it? If you're not sure you can get a high-quality, properly selected, location-specific valve installed on a job, then by all means specify quality pressure-independent valves. It should be well worth the customer's investment.
We are now going to discuss the use of buffer tanks in a chilled water system. Specifically, we'll be focusing on 3 key points. The first is, why might it be necessary to install a buffer tank? Followed by, when should one design into the system? And finally, how big should the buffer tank be to adequately serve the chilled water loop? Well, the purpose of a buffer tank is to ensure stable control of the chiller. When a chiller is connected to a short chilled water loop with a low volume of water, the leaving chilled water temperature control may become erratic due to rapid changes in the return water temperature. The buffer tank serves as a means to increase the volume of water in the chilled water loop. With the increase in volume, the time it takes for the fluid to leave the chiller, move through the system, and then return to the chiller increases. The time that it takes to make this cycle is called the loop time, and it is measured in minutes. A buffer tank, sometimes referred to as a storage or an inertia tank, is a common solution to short water loops that do not meet the minimum loop time suggested by the chiller manufacturer. This typically occurs when the system has only one chiller and one or two closely coupled loads. For optimal performance, it is recommended that the storage tank be located upstream of the chiller and the chilled water pump. In a primary-secondary system, this ensures that the buffer tank's water is integral to the chilled water loop and will provide the minimum loop time as necessitated by the chiller unit controller. The minimum loop time varies between chiller types as well as chiller manufacturers. And typically, minimum loop times are in the range of 1 to 5 minutes. You will want to confirm with the manufacturer what the actual loop time requirements are. Additionally, some manufacturers may offer a factory option that includes a buffer tank size to meet the minimum loop time requirements. Here's an example of a Trane air-cooled chiller with the buffer tanks installed in the end of the unit. This will reduce the installation time in the field. So how does one determine if a tank is required and how big it should be? First step is to determine what the required volume in the chiller water system must be in order to meet that specific loop time. The calculation is pretty straightforward and is simply the chiller's design flow rate in gallons per minute times the required loop time. For example, chiller that has a 500 gallon per minute and requires a 2-minute loop time will need to be installed into a system with a minimum of 1,000 gallons. You will then need to determine the actual system volume. This is the total amount of fluid in the system, including all of the coils, the pipes, the evaporator, etc. If the system volume is less than the required volume, a buffer tank should be added to increase the amount of fluid in the system. The size of the buffer tank would be the required volume minus the system volume. Another method to increase the volume without the use of a buffer tank would be to increase the pipe diameter to allow for more fluid in the system. If a buffer tank is required, consider looking at alternate chiller conditions. A chiller's flow rate is inversely proportional to the delta T. So if you can design a chiller with a larger delta T, the required volume will reduce and may eliminate the need to add the buffer tank to the system. To summarize, the purpose of a buffer tank is to ensure stable control of the chiller. Buffer tanks are installed when the system's loop time is lower than the loop time required by a specific chiller. The size of the buffer tank is determined by calculating the required volume to meet the loop time and subtracting the actual system volume from the required volume.
Thank you, Justin. We've just covered many of the component-specific decisions. Now let's move on to a couple of the more advanced considerations. Mick is going to get us started with some guidance on variable condenser water flow and system performance.
We continue to receive a lot of questions on whether a variable speed drive should dynamically modulate condenser water pump speed to attain better system performance. We covered this in a lot of detail in our 2013 E&L on all variable speed chilled water systems, so afterwards you can view it for the details. Let's summarize what was covered. In order to properly apply dynamic condenser water pump control takes some work. First, the flow rate has to stay above the minimum flow rate as defined by the highest of minimum tower flow, minimum chiller flow, or to produce the static lift in the open portion of the condenser water system. Then, at each operating point during the year, determine the optimal condenser water pump and cooling tower fan speeds, and make sure you don't reduce the pump speed at conditions that will cause the chiller to surge. Finally, make sure the sequence is documented and properly commissioned. Let's look at the examples we shared in 2013. We'll start with a system that has variable speed drives on chillers, variable speed drives on cooling tower fans, condenser design flow rate of 3 GPM per ton, a constant flow condenser water pump, and control to arrive at a cooling tower set point that minimizes the sum of chiller plus tower fan energy. This plant is already pretty good, just under 0.55 kW per ton annualized performance for the chiller, condenser water pump, and cooling tower fan. What if a variable speed drive is put on the condenser water pumps? There's a decent amount of savings, as the annualized plant performance is now less than 0.53 kW per ton, a 3.7% annual reduction of the chiller, condenser water pump, and cooling tower fan energy. So the control complexity of applying a variable speed drive on the condenser water pump may be worthwhile. But there's a simpler option that nets similar savings. At 3 GPM per ton, the design condenser water temperature difference is about 9.4 degrees Fahrenheit. Today's industry recommendations include the ASHRAE Green Guide with condenser water delta T's of 12 to 18 degrees. Consulting engineers Kelly and Chan, 14 degrees. And Steve Taylor, in his December 2011 ASHRAE Journal article, 15 degrees. Those result in the flow rates shown in the rightmost column. Clearly, the industry is recommending that systems be designed with significantly lower condenser water flow rates. So let's look at that same system with a constant flow pump and a lower design condenser water flow rate. In this case, 2 GPM per ton. The performance is calculated using the same pipe sizes as the 3 GPM per ton system. With constant flow condenser water pumps designed at 2 GPM per ton, the annualized system performance is a little bit better than the higher design flow rate and dynamically varying the pump speed. But the important point is that the savings can be achieved without any control complexity, just by designing the system per the industry recommendations. In addition, the pump is smaller, so the installed cost goes down a little. Now, what if we combine the two and employ both industry recommended design practice and dynamically varied the condenser water pump speed? The savings are minimally better than constant flow. Well, the values in the previous slide were for a hospital in Memphis. When you view the 2013 E&L, you'll see that we looked at varied climates, including Chicago, Memphis, Albuquerque, and Miami. We also examined both hospitals and office buildings to account for different load profiles. In the different buildings and locations, sometimes dynamic control with a higher design flow rate was a little better, and sometimes lower design flow with constant speed was a little better. But in every case, the performances were almost the same, with one exception. The one difference was in Miami, where a variable speed drive on the condenser water pump gave virtually no savings, no matter the design flow rate. Here's some guidance on the condenser water design and control. In existing systems designed at higher flow rates, variable condenser water flow offers savings, except in climates that are humid all the time. In other climates, you can decide if the controls and commissioning complexity are worth it. To keep things simple and still achieve savings, on new jobs, design the condenser water systems to the industry recommended flow rates of 1.7 to 2.3 GPM per ton. Using a constant speed pump, the savings are very similar, the installed costs go down a little, and very importantly, the system control is simple. There are very small additional savings available by designing to these industry recommended flow rates and dynamically controlling the condenser water pump speed.
Next, we will look at the impact on chiller performance based on how chillers are piped in the system. Before we do this, let's revisit the fundamentals of chiller performance. There are the two factors that impact chiller performance. The first is the amount of load the chiller has to satisfy, and the second is the lift a compressor must generate. The amount of lift is the difference in refrigerant pressure between the evaporator and condenser. the refrigerant pressures are proportional to the temperature of the refrigerant. Therefore, the colder the evaporator and the hotter the condenser refrigerant is, the higher the lift. Finally, the chiller kW is proportional to the amount of load and lift. If one can reduce the lift, the chiller kW will also come down. So now let's look at a common way to install chillers in a multiple chiller plant. Shown here is a pair of chillers piped in a parallel arrangement and manifolded into a common supply header. Each chiller has its own dedicated chilled water and condenser water loop, and the chillers are designed to produce 37-degree chilled water with a 55-degree return temp. The condenser side was designed to provide 85-degree water from the cooling tower and return that water at 98.9 degrees. Recall that the lift is proportional to the leaving condenser temperature minus the leaving evaporator temperature. So for this design, the amount of lift on each chiller is 62.9 degrees. Now, let's look at an alternate method of piping the chillers and the effect that it has on the lift that the chillers must generate. You'll see in this arrangement, the chillers are installed in a series configuration. Both chillers share a common evaporator and condenser loop. When installing chillers in series, it is important to design them for counterflow. This ensures that the downstream chiller that has to make the coldest supply water, in this example 37 degrees, receives the coldest condenser water. By installing the chillers in series, you create two levels of thermal staging to help reduce the lift on each of the chillers. The upstream chiller receives 55-degree return water and satisfies about half of the load. In this configuration, the upstream chiller only needs to make 45.1 degree fluid instead of the 37 degrees. The downstream chiller then receives that 45-degree fluid and conditions it to the 37-degree supply temperature. On the condenser side, the flow goes the opposite direction. Now the downstream chiller receives 85-degree water and raises it up to 91.3 degrees. The upstream unit then further increases the condenser temp to 98.9 degrees. By installing the chillers in series counterflow, we still meet the same design conditions and temperatures, but the lift has been reduced by over 8 degrees, which is a 13% reduction. Recall that chiller kW is proportional to the lift, so that is a 13% reduction in chiller kW. When designing a chilled water system, you must also consider the entire system performance. So while the chiller does become more efficient, there will be some pumping penalties based on the additional pressure drop of pumping through both chillers. In order to minimize the pumping energy, it is common to design series systems with large delta T's, usually in the range of 15 degrees or more. One may also consider utilizing single-pass evaporators and condensers. Another factor to consider is the tonnage of each chiller. You can design the system with each chiller handling 50% of the load, but it can be done more efficiently if you optimize the split. Typically, an optimized split is where the upstream chiller is designed to meet about 53% of the load and the downstream makes the remaining 47%. Designing the system this way ensures that both machines can make the 37-degree supply temperature in the event the downstream chiller is down or being serviced. Now, let's take the same design utilizing a Trane duplex chiller. And these chillers are essentially packaged series counterflow chillers. If we install a pair of duplex in series, you get 4 levels of thermal staging. Now you'll see that the lift is further reduced down to an average of 50 degrees. That results in a 19% reduction in lift over the base parallel configuration. To summarize, the amount of energy a chiller consumes is directly proportional to the lift that the compressor has to generate. There are a number of ways to reduce the lift on the chiller, and one of them is to simply stage the equipment in a series counterflow arrangement. Recall that at the design conditions of 37 degrees supply and 98.9 leaving condenser temp, that chillers installed in a parallel arrangement have to generate 62.9 degrees of lift. Installing the chillers in a series counterflow arrangement creates the thermal staging and reduces the lift down to 54.5 degrees, resulting in that 13% reduction, and hence a 13% less energy usage. And for larger systems, installing duplex chillers in series creates 4 levels of thermostaging, and lift is reduced down to 50 degrees, which is a 19% reduction in lift and energy simply due to how the chillers are piped in the system.
We've discussed how higher delta T's can minimize overall system energy. If designing a system with a delta T more than 14 degrees, you've probably made the decision to use a series chiller plant. In this section, we will cover how series chillers should be controlled and discuss how the compressor type might affect control strategy. A discussion on how to control series chillers will lead us through 3 topics: what set points to use for each chiller, how to sequence the chillers, and any loading strategies like preferential loading or equalization. For what follows, we will assume variable primary flow. In addition to reduced chiller pressure drop, a variable primary flow system helps with set point control and upstream chiller efficiency. Temperature control can be executed in several ways. The image shows a strategy where the controller on each chiller is set at the system design set point. In this layout, either chiller can be used to meet the system demand for up to 50% of the system load. As system loads greater than 50%, the upstream chiller is preferentially loaded because it will attempt to produce the design leaving chilled water temperature. Any portion of the load that remains is directed to the downstream chiller. Another method is to stagger the set points. With staggered set points, the downstream chiller is generally operated first. The upstream chiller operates at a warmer temperature, which allows it to operate at a higher efficiency. With a series configuration, the controller should calculate and send a unique chilled water set point to each of the chillers based upon the system chilled water set point and the position of the chiller, upstream or downstream. To implement staggered set points, the downstream chiller is operated to the system supply water temperature, and the upstream chiller set point is dynamic to balance the loads on the chillers when both are operating. The simplest way to do this is to have the chiller plant control system dynamically change the upstream chiller set point to be halfway between the chilled water return and supply temperatures. For example, if the chilled water supply temperature is 42 degrees and the return temperature is 50 degrees, the upstream chiller set point should be 46 degrees. In a prior section of this broadcast, Justin used a slight variation to this halfway recommendation. He recommended loading the upstream chiller for 53% load and the downstream chiller for 47% load. We use the halfway point here for simplicity, but do note that there are opportunities to optimize. When a chiller is preferentially loaded, it is to be operated at full capacity while the remainder of the load is handled by the other chiller. When the total cooling load on a plant is greater than the design capacity of either individual chiller, both chillers will operate. Preferential loading is desirable for systems with a heat recovery chiller or an absorption chiller in the upstream position. Unloading of the upstream chiller can be accomplished by giving both chillers the desired system chilled water supply temperature as their set points. Here, an absorption chiller operating at a higher temperature becomes more efficient and can deliver more cooling capacity. Most systems will utilize equal loading to maximize efficiency. As previously mentioned, equal loading of the 2 chillers may be accomplished by using a chiller plant management system to dynamically reset the upstream chiller set point in response to changes in system load. So how do we sequence chillers piped in series? In most cases, start one chiller, upstream or downstream, it doesn't matter much, unless only one is more efficient or has a VFD, then start that one first. When the first chiller runs out of capacity, start the other chiller in the pair. When the first chiller runs out of capacity, start another series pair. From then on, add and subtract capacity as series pairs. There are always exceptions, but this is the general sequence. There is one other very important control issue, and it is dependent on the mechanism used to unload the chiller. Centrifugal and helical rotary chillers unload continuously, so the leaving water temperature can be maintained close to set point. Chillers with scroll compressors, however, unload in a stepped function. Compressors are turned on and off to satisfy load. When they do, the leaving water temperature cycles between 2 points, one above set point and one below. but on average, the set point is maintained. When scroll chillers are piped in series, this step behavior causes a number of issues. Let's consider an example where the upstream chiller set point is 50 degrees and the downstream chiller set point is 42 degrees. Let's say each scroll chiller is operating 2 compressors, but the load goes up and the downstream chiller has to turn on another compressor when its leaving water temperature is 43 degrees. With stepped unloading, that compressor operates at capacity and the leaving water temperature drops below 42, let's say to 40 degrees. This causes the return water temperature to the upstream chiller to drop, so the upstream chiller turns off one of the compressors. Now, the upstream leaving chilled water temperature rises. At some point, it rises far enough that the upstream chiller's second compressor comes on again. That decreases the temperature entering the downstream chiller, and with 3 compressors operating, its leaving temperature drops far enough, causing one of the downstream chiller's compressors to cycle off. Therefore, the upstream and downstream chiller hunt, with compressors on both chillers being turned on and off. A simple way to mitigate this issue is to give both scroll chillers the system water temperature set point. When the load is above the capacity of one chiller, the upstream chiller runs at full load and the downstream chiller cycles its compressors, but they do not fight one another. Some people get concerned that this may impose more load on the downstream chiller. However, to allow the run hours to equalize, the upstream chiller can be designed as the lead chiller half the time and can be only one operating when the load is below the capacity of a single chiller. So let's review. With chillers in a series configuration, set the downstream chiller set point to the system's supply water temperature. When both chillers are operating, the upstream chiller set point depends on compressor type. If the chillers are centrifugal or helical rotary, have the chiller plant controller dynamically reset the upstream chiller set point to balance the load. If the chillers have scroll compressors with stepped unloading, set the upstream chiller set point to the system supply water temperature. Sequencing is fairly straightforward. Simply start the chiller that's most efficient, and once a pair of chillers are running, start and stop chillers in pairs from then on.
Our next and last question today is, compared to operating 1 pump, will operating 2 pumps at lower speed save energy? Now, this came up during an ASHRAE conference conversation with respect to the affinity laws. And Dick Pearson, a wise consulting engineer in Madison, raised his eyebrows and said one word: think. So we did. As it turns out, the reason the question is asked is because of a misunderstanding or perhaps lack of thinking about the pump or affinity laws. The pump laws describe the relationship between flow rate and power. And in a straight pipe, that relationship is cubic. So the thought process is, if an additional pump is enabled, the flow rate per pump will go down, and the kW per pump will go down with the cube of that flow rate. But this just isn't true, and is an improper understanding of the pump laws for this situation. What did we miss? The pump laws describe what happens when the system flow changes and all the system pressure drops change in response to the flow changes. But at any point in time, whether 1 pump or 2 are operating, the system flow rate stays the same. The only thing that changes is the flow rate is divided between 2 pumps. Let's look at that to understand what actually occurs. The pump power equation is shown, and pump power is dependent on the flow rate and the system pressure drop. 0.746 and 3960 are conversion factors. In the denominator are the pump, motor, and drive efficiencies. They may improve or worsen at different pump operating conditions. Now let's look at a system. The system flow rate is identical no matter how many pumps operate because it's dependent on the required coil flow rates. So we have the same flow rate through the coils and valves as well as the pipes, elbows, and fittings. That means their pressure drop is the same. The flow rate through the chillers also remains identical, as does their pressure drops. The only change in the system is that there are now 2 paths for water flow across the pump manifold. Simply put, when the flow rate through the operating pump is reduced, so is the pressure drop through its fittings and the pump itself. So there is a pressure drop reduction, but it is only the pressure drop from the return manifold to the supply manifold and through the pump. How about pump, motor, and drive efficiencies with two pumps operating? Bert Rischel's ASHRAE Journal article titled Wire to Water Efficiency of Pumping Systems shows there are some operating conditions that allow the combined pump, motor, and drive efficiency to rise when more pumps operate. Now, we don't have time to get into all the details today, and it takes some work on your part, but if the combined efficiency is higher, pump power is lower. So is operating an additional pump beneficial? The system flow rate doesn't change. Almost the entire system pressure drop is identical. There's only a small change in system pressure drop between the pump return and supply manifold, and without study, we don't know if the pump, motor, and drive efficiencies are better or worse at reduced pump speed. Now, as long as combined efficiency is the same or better, the result is pump power that is a little lower due to the system pressure drop being a little lower. So operating an additional pump is likely okay, but the savings are not even close to the cube of the flow. So just remember the advice. Think.
Thank you, gentlemen. That is all the time we have today. Hopefully, we provided you with some guidance to help you make decisions that will benefit your customers on your next chilled water system design project. As always, a bibliography is included in your handout and provides more information on where to find a number of the resources related to all of today's topics. Or contact your local Trane account manager for specific information on chilled water system design. For those of you seeking continuing education credit, be sure to check out our continuing education programs, which include many past E&Ls, all free and on demand. And please remember to fill out a survey and let us know what you think of today's program. AIA members, remember to turn in your member information to your local site coordinator. And finally, please ask your local host about details for the remaining Engineers Newsletter Live program this year. Thanks for your time today. We look forward to seeing you next time.